In this lecture, we will try and understand what is classical normal linear regression model. I'm going to focus a lot on the normality of the parameters. Now, what is known as the classical theory of statistical inference has two main branches, and I will help you recall the first one. So this classical theory has two main branches. The first one is called estimation, and the second is known as hypothesis testing. What are these two things? Let us try and understand. Estimation is when you estimate these betas. So for example, this is what we have been doing in the previous modules. When you go ahead and say that, your consumption is minus 200 plus 0.9 y, you are estimating beta 1, you are estimating beta 2. For any value of income that I give to you, you will be able to tell me that this is the amount of consumption that is going to take place. That is estimation. Estimation is understanding and calculating what is beta 1 and what is beta 2. But there is more to it. There are two main things that I want to understand beyond this. The first thing that I want to understand is that once I have estimated beta 1 and beta 2, actually because I am estimating it for a sample, I am estimating beta 1 hat and beta 2 hat, how close is this beta 1 hat and beta 2 hat to the actual beta 1s and beta 2s? How closely do these beta 1 hat and beta 2 hat represent my population? That is the first question that I have in mind. I have estimated it, but how close is my estimation to the actual values? What do I see in the population as a whole? Is it really the case that when income increases from 1,000 to 2,000, that consumption increases 90 times? 0.9 times by 90%. Is that really the case or not? So I have to see how close my estimation has been to the actual parameters, to the actual betas. That's the first thing that I want to understand. But I also want to understand, does this beta 1 and beta 2 actually have an impact on my Y? By which I want to actually go ahead and understand whether beta 1 and beta 2 are significant or not. Let me reframe this. I understand that the relationship that I have got is minus 200 plus 0.9 times income. I want to go ahead and understand whether this beta 2 is statistically significant or not. And when I say whether this is statistically significant or not, you can come up and say that yes, it is, or no, it is not. I am also going to ask you at what alpha level. Are you saying you are 95% confident that, income actually has an impact on consumption? Are you saying that you are 90% confident? Are you saying that you are 85% confident? Are you saying that you are 99% confident? At what level did you went ahead and you tested the significance? Something for which you have to recall your t-tests, z-tests, and when I go to multiple regression model, your chi-squares and f-tests. Because that is what hypothesis testing is all about. So, my null hypothesis will be that beta, I'm going to take this as beta naught and I'm going to take this as beta 1. So beta 1 not, beta 1 equal to 0, sorry. And my alternative hypothesis is going to be beta 1 not equal to 0. So ideally, what I am doing here is that if I reject my null in favor of alternative, I am saying that yes, income in fact has an impact on consumption. But if I do not have sufficient evidence to reject my null, then in that case, whatever be this value, I cannot say that when income increases, consumption increases, because this is not coming out to be significant. So I have to really go ahead and do a hypothesis testing to check the significance of these betas. I am not okay with just going ahead and saying that beta is 0.9 or beta is 0.8. When income increases, your consumption will increase 80% or 90%. Is that in fact significant or not is something that I am interested in. So let's go back and tell that there are two main things that we have to do. One is estimation. That is something that we have been covering by far, where we have already gone ahead and understood how to calculate beta 1, how to calculate beta 2, how to calculate sigma square, etc. But I have to also go ahead and understand the hypothesis testing part. We were also able to show that the estimators of the parameters were okay. Now this is something that we have done that, and I'm going to recall this again and again, where we estimated that and we showed that these estimators have blue properties. What was blue? It was best linear unbiased estimators with efficiency, and by efficiency I meant that it had the minimum variance. Now, as I just highlighted, estimation is half the battle. We have just done half the thing, that I've gone ahead and calculated that this is the value of my parameter. But I have to go ahead and test whether the parameters are significant or not. Only if the parameters are significant, I would be able to say that yes, in fact, there is a dependency of consumption on income. And only then I would be using it to draw inferences about the population regression function. Something that we have done as part of chapter 2, where we went ahead and found out some inferences. But to actually draw inference, we have to do hypothesis testing. So we would like to find out, one, how close my beta 1 hat is to its actual beta 1, how close beta 2 hat is to its actual beta 2, sigma square hat is to its actual sigma square, and then I would like to understand if beta 1 not equal to 0, beta 2 not equal to 0, do I have sufficient evidence for this or not? To go ahead and do any of those, the first stepping stone that we have is to try and understand the probability distributions. Because of the randomness in these variables, because I understand that beta 1 hat, beta 2 hat, and sigma square are random variables, they have probability associated with it, that with this much probability, beta 1 hat will be this much. With this much probability, it is going to be this much. We have to find their probability distributions. I would like to, throw some light and, on the importance of statistics throughout the course, because, random variables, what is a random variable, what is a probability distribution, is something that is a major part of the statistics course. So, it is always a good idea to take statistics simultaneously or go through at least the major concepts of statistics. Probability distribution of disturbances. Specifically, this is something that we went ahead and proved in chapter or module 3, where I talked about deriving beta 2 hat. And we said that beta 2 hat can be specifically written as summation xi yi upon summation xi square. You can go ahead, to the module and see that we derived that beta 2 hat can also be written as summation ki ki is xi upon summation xi square. Since the x's are assumed to be fixed, that is something that we have been assuming for now, that they're non-stochastic, they're non-random in nature, conditional on the fixed values of x's, this equation shows that beta 2 hat is linear function of yi. Obviously, I'll give you a very simple example to understand linearity. When I say that x is a times y, or let's say y is a times x, there is a linear relationship between the two. When I say y is ax square plus ax plus b, or you can take this as bx plus c, this is a quadratic relationship between the two. When I say y is ax cube plus bx square plus cx plus d, there is a cubic relationship. When I say y is equal to 1 by ax, that's also a linear relationship. But when I say y is equal to a1 by x, that's a reciprocal relationship. So here, because I could just simply say that beta 2 is k times y, it's a linear relationship. So, from this equation, I understand that beta 2 is a linear function of y. Y is a variable, definitely. As y changes, beta 2 will change. But this part here is constant or non-random because this part just consists of x's. And we already know that x's are fixed. X was just 80 or x was just 100 in case of income consumption example. Income was held at a single value, like income was always 80, and for that 80 we had different y's leading to different betas. For income level equal to 100, we had different y's. So, here I understand that beta 2 hat is a linear function of yi, which is random, definitely, because y is random, because y has two parts to it. Yi is actually e of y given xi plus ui. This itself is random in nature. The errors are random, and that generates yi to be random, right? Okay, so since yi is beta 1 plus beta 2 xi plus ui, I can here replace this yi by this value, and I get beta 2 hat is equal to ki, summed up ki, summation ki, beta 1 plus beta 2 xi plus ui. Because ki's, betas, xi's are all fixed, beta 2 hat is ultimately a linear function of random variable ui. Now, be very sure of what we are doing here. A lot of students get confused that, when you just started this lecture, you told us that, betas are not fixed, they're random. That is why you're finding the probability distributions. And now you're telling us that these betas are fixed. So, there is this confusion that exists whether betas are fixed or non-fixed. Well, understand that I am replacing it by its PRF, population regression function. In the population regression function, the betas are fixed. I for sure know the clear relationship that exists between y and x for my population. I am using sample to estimate the population. Here, the equation that I had written was for my sample. For my sample, If I pick up one sample, I get one beta 2 hat. I'm deriving this sample from a population. Instead of deriving this sample, if I derive some other sample, I get some other beta 2 hat. If I derive some other sample, I get some other beta 2 hat. So these are random in nature because I'm randomly generating sample, and for each sample, I generate its own beta 2 hat. But when I take population as a whole, it just has one beta 2 and one beta 1. So the equation for the population is beta 1 plus beta 2 xi plus ui, where these beta 1s and beta 2s are non-random or fixed. But beta 1 hats and beta 2 hats, they have a probability distribution associated with them, or they are the one which are random variables, which are random in nature. If I go back and look at this, I've replaced my yi. I said beta 2 hat is a function, linear function of yi. In fact, it is summation ki yi. It's a linear function of yi. I replace this yi by its PRF. In the PRF, beta 1, beta 2 is fixed. Xi obviously is fixed. It's non-stochastic. Non-stochastic, non-stochastic, stochastic. The only thing that is bringing randomness is this error term. Because the only thing bringing this randomness is the error term, I am saying that all the randomness in beta 2 hat is due to ui. So the probability distribution of beta 2 hat and also beta 1 hat will depend on the assumptions that you make about the probability distribution of ui. Very, very important.